Hi there, my name is Carmina, and I'm happy to be here as your host for today's virtual seminar on delivering quiet power to automotive electronics, brought to you by Keysight and co-sponsored by Newark and Picotest. Joining us today is Heidi Barnes. She has over 30 years experience in our industry. She enjoys writing, simulating, measuring in all forms of water sports, such as underwater hockey, which is not much different from designing at high speeds. Both require skill. Most signal integrity engineers have been working in this industry a long time. Speed, a fast simulation tool, is essential. Teamwork, communication with your design, fabrication, and manufacturing teams is critical. And the ability to hold your breath for long periods of time as you wait for working prototype to come back. I love working with Heidi and always look forward to her presenting. Heidi, you now have the floor.
Thank you, Carmina. That was a great introduction and very, very fun to compare it with my underwater hockey sport, which I do love very much, just as much as I do love the challenge of designing power integrity and in this case, delivering quiet power to automotive electronics. So let's go ahead and jump right in with our presentation. The style today, we are doing because of the COVID epidemic or whatever, we can't do things in person. So I'm going to try to make this sort of interactive and live with some demos and not just slide presentations. So I hope you enjoy the format today. And I really want to talk about a lot of the things that I have learned about power integrity. I used to think it was easy. It was just DC. But more recently, as voltage levels drop, as the dynamic current goes up, we have some new challenges. And with high-speed digital, power delivery to high-speed digital systems, it is not just DC. It's fast delivery of power at microwave frequencies. And really, if you look at it, this is sort of the automotive challenge where for AI and a lot of the intelligence that's being put in autonomous vehicles, the intelligence that's being put into the electronics of modern automobile systems, it's incredible. And you'll see that you have multiple microprocessor units, different sensor systems. They all have communications, and a lot of that data is being uploaded to the cloud or even processed locally by FPGAs and local systems. So in terms of the power delivery, we have to get power to all of those different components. And so they make use of multiple point-of-load power supplies. Your automotive electronics does not all just run on 12 volts. It has to be converted down to the 1 volt or 0.8 volts that a lot of electronics run at today to conserve power. And although the voltages are dropping, which can reduce the power, we still have very high DI/DT switching loads. Lower voltages mean we have less margin on the amount of ripple that we're allowed on that power rail. And in the power integrity world, we'll learn about that today. Target impedance is important to reduce help control or reduce that power rail ripple. We try to reduce that or keep that impedance at a target level. Things like power supply rejection ratio can help to avoid noise from one power delivery point of load contaminating another system, say for a clock system, a phase lock loop, or maybe you have a video system that's you don't want contaminating other communication systems. So here, I do want to stop real quick and just point something out. If you are new to power integrity, or maybe in your industry you have some different terminology, I apologize. I will be sort of using interchangeably a couple of different terms for the how I call the power supply. And here I like to say a point of load power supply is typically a switched mode power supply, SMPS, with a buck regulator DC to DC converter design that the microprocessor PCB world often calls a voltage regulator module. So I will be using a couple of these terms. They basically all mean the same thing. It's that a part of the electronics that's delivering power to the load. And the key takeaway here, just again, power integrity engineers need RF microwave design tools and measurement tools to tackle the new challenges of power delivery for high-speed digital electronics. Okay, this is a board that we're going to jump into right away. This is the Zinc ZCU 104 characterization board. It's an FPGA board that Xilinx actually sells. It's not too expensive. You can buy it from companies like our partner Newark, or vendor distribution companies like Newark Electronics. And they're actually sponsoring our presentation today, along with Picotest. And this board here, we actually worked with Xilinx, and I worked with Steve Sandler of Picotest for a paper at DesignCon this year. And we picked up this board and said, hey, let's go ahead and analyze VCC int and see what we get. And the exciting thing, you can see we've got some cables here for measurements. We actually hooked it up to a bench supply to do the analysis for VCC int. But I'm going to show you in about 10 minutes here how easy it is to get this board imported into a simulation tool, actually do an DC and AC analysis, and then bring that EM AC model into a schematic and run a full PI ecosystem simulation. And what was exciting is that when we did this analysis, we didn't really know what we'd find at first. But what was very interesting is when I first hooked up to do measurements and look at power rail noise, I was sure that the higher frequency, 200 megahertz rail, than down at 30 megahertz with only 2.5 amps. And boy, was I wrong. So why? How come? Why is there more noise at 30 megahertz with lower current than at 200 megahertz? And so the key takeaway here is that the dynamic current and voltage at the FPGA pins, by doing simulation, we can actually find and verify the worst case noise on the power rail. So let's go ahead and see how we actually did this. And that's like, I'm going to start off with that demo, kind of jump right into what it means to do a power integrity analysis and really look for that worst case power rail ripple and how to get a quiet power delivery. Then we're going to go with the agenda today. I'm going to jump into some specifics, what you really need to know about power integrity. These are some key items that I have learned from Steve Sandler of Picotest. Steve Sandler has been in the industry for over 40 years. He's designed power supplies. He's written books on power integrity. He's a prolific author for magazine articles and webcasts and different things. But these are some of the very critical items that we feel are important in simulating the power integrity ecosystem and the benefit that simulation and measurement can provide in providing a robust signal or power integrity design. And then we'll kind of conclude with the solutions that we have there, the simulations and measurements available for power integrity at Keysight. So let's go ahead and jump in here. Before I start the demo, I do want to do a real quick review of what a power integrity or a power electronics engineer usually does. The key thing here, it's all about the load. We want to deliver quiet power to the load. Well, what does that mean? It means that I pull out my oscilloscope and I put a probe on that power rail and say how much noise is there. And here's a screenshot of a real-time oscilloscope, and the yellow is the voltage ripple versus time. The blue down below shows my load, the dynamic current. And if I apply a step load of current change, in blue down here, I will get a corresponding ripple on my power rail. That is considered the natural response. This step load current is what most data sheets say. They will provide data that if you do a step load with this certain ramp rate or rise time, then your power rail or our voltage regulator can regulate the power, and your ripple will stay within a certain specification. But what they don't tell you is that if you look at that natural response and you see some ringing, if you actually turn the load current on and off at that at the frequency of that ringing, you get a forced response. The forced response is much bigger than the natural response. It turns out it's actually the Q, or the sharpness of that resonance times the natural response will give you an estimate of the a maximum of the forced response. So it's an exponential increase here, and then it levels off. But look at this forced excitation here on the current. That looks like digital data. If I didn't know better, this could be maybe power on off, maybe some bursted data. So I can get a very broad spectrum of frequency content with my load. And so the question is, how do I figure out what the worst case is? And if I do a forced response, I might actually have a failure. So let's go ahead and go to the next slide here. So what we use in the power integrity world, and this there's been numerous books. Eric Bogatin has talked about target impedance. Steve Sandler, obviously, with his books on power integrity. This is a very popular way of looking at how to deliver power for high-speed digital systems where there's a very broad spectral content for the power delivery. And what they basically came up with is sort of a very simple rule of thumb that said, what's the maximum ripple I'm allowed, the delta ripple, plus or minus 5% of my power rail usually, but that millivolts of ripple that I'm allowed divided by the delta step in current that I expect. What's that transient step in current that my load is going to have? If I divide that ripple voltage by the load transient, I will get a target impedance. I sometimes like to look at this equation in reverse, saying that if I have a delta change in current times that impedance of the power rail, I want to make sure that that doesn't exceed my ripple. And if I actually look at a real board and how I use this target impedance, we're going to talk a lot about why we want flat impedance, not just staying below that target impedance. So if my current times that impedance stays below the ripple, that sounds great. But what you find is if I can maintain an impedance over frequency that's relatively flat, there's a expert on power delivery and power electronics, power integrity, Madhavan Swaminathan from Georgia Tech. And in his book, in the very first chapter, he comments that the minimum number of capacitors to achieve that target impedance is a flat impedance design. That sounds great. If I can minimize the number of capacitors to achieve a target impedance, that is less money. That's exactly what I want for my design. It's lower cost. Fewer components also means fewer solder joints, higher reliability. And here you can see an example of an FPGA high-speed digital board here. And we've actually simulated the power delivery network with all of the capacitors, and we're plotting the impedance versus the frequency. We've drawn a region of flat target or a target impedance region, and we're trying to keep the impedance of our power delivery network below that target impedance, and not just below. We want to keep it flat. Now, we also talked about resonances, and we're going to learn more later on about how flat impedance gets rid of those resonances in the power delivery network, and we avoid that worst case ringing of a forced response. And in that way, we can ensure a robust, quiet delivery of power. Now, you'll see some breakpoints out here as we go up in frequency, and we're going to learn some more about that. We're going to talk about how we get this target impedance. But basically, just remember that our load doesn't have infinite spectral content. At some frequency, our load does not have any spectral content at those higher frequencies, and also that spectral the higher frequencies can't get into or out of the package. And so that's some of these breakpoints that you're seeing at the higher frequencies. So the key takeaway here is that flat impedance design over a wide bandwidth gives the best performance, and that's what we're going to be learning about today. So now we're going to jump in. You've got the basics. We learned about just the basic natural and forced response when we measure power rail ripple with a real-time oscilloscope, and we also learned about target impedance. So now let's go ahead and share my screen, and we're going to jump right into a demo. Okay, let's go ahead and jump into our ADS workspace. So if you open up ADS, you get what's called the ADS main window, and this helps organize I have a folder with all of the different analysis schematics, layouts, data analysis in here, and it can get quite complicated. So what I've done is ADS lets me use a hierarchical schematic. So just like electrical engineers are familiar with schematics and they have hierarchy, so each one of these blocks here is a sub-schematic. Some of them are for EM, some of them are for models, PI ecosystem. But if we're going to analyze our ZCU 104 board, the first thing we need to do is import that board. And here you can see the board has been imported. We actually have, it's very easy to import, just a simple import, and you can bring in .brd files or ODB++. I always recommend when you do an import, it's going to bring in all the net names and the components, but you always want to look at the stack up and just make sure that it imported correctly, that you have the right material properties, and that things imported. Because sometimes the import standards are the ODB++ and the .brd standards, or the data may not be complete. So always check that substrate. Then what we want to do is open up an EM analysis. We can go to what we call SI Pro and PI Pro. This is our power integrity EM simulation tool. It also does DC analysis. And we're just going to go ahead and start a new analysis of this board. And this is a net-based tool, so when it brings in the board, it's actually going to bring in all of the net names and all of the components. And that makes it easy so that when I select a component or select a net, it will automatically place the pins for me for the EM analysis and for the DCIR drop analysis. And that way, I don't have to be an EM expert and know how to set up ports. It's going to do a lot of that automatically for me. This is a very graphical system, so we're going to go ahead and I'm going to start with a clean analysis setup here. So here's the board that's imported. This is the board I just showed you, the Zinc ZCU 104 board. And you can see it's, I think, about a 14 or 15 layer board, and has the FPGA is U1 here. But to do an analysis, we have the board imported. We can see all of the net names. We can see all the components. And it's actually smart enough to have found, using the names that are on these nets, to identify ground and power nets. So that's already done for me. But I can go down to analysis, and the first thing I recommend is a DC analysis, because we want to make sure the board imported, it's really easy to understand the DCIR drop, and we can make sure that everything is working as expected. So all I have to do is click on the VRM. I know this is my VRM I want to analyze. I could also search for it by name, but it finds it for me in my component list. And then I right-click and say Create VRM for analysis, and I want to analyze VCC int. This is the main power rail. Next, I need to add my sync, so I click on U1. I right-click and create sync for analysis. I again want to find my VCC int power rail that I want to simulate, and I find the ground, corresponding ground that I want to use. Now I've added my VCC int power rail and my grounds, but you'll notice there's a warning saying that the VCC-INT switch power rail is not connected to VCC-INT. So I need to make sure that my VRM is connected to my sink. So I have to find the component that connects those two. So I can say, where's the component that connects those two nets? And that finds the inductor here that connects my VRM to the power rail going to the sink. And again, I can just right-click on that highlighted component and create component model for analysis. If I double-click on that component that was just created, I can add a lumped model very easily. I can say it's 5 milliohms of resistance for the DCIR drop, and I can make that lumped model my default and apply, and I'm done. I want to set up my VRM, so I double-click on my VRM, and I can set that to the 0.87 volts of this power supply. I can use maybe a 5% ripple tolerance here, or DCIR drop tolerance, and apply that. I can also set the current draw, and I could do, sometimes I do, if you know the current you're interested in, sometimes I just put 1 amp because it's easy to do the math with that. We also allow for symmetric tolerances and asymmetric tolerances now, which can be very powerful when analyzing multiple power rails at the same time. But here we go. Now you can see this is set up. We have a VRM, we have a sink, and we've identified any components that are connecting those two, the VRM and the sink together. Under options, it's a fairly simple setup for the DCIR drop. If I want to get a very detailed analysis, I could include the resistive losses in ground. But in this case, I have very large plane layers, and if I want to speed up the simulation, I can just look at the resistive losses in the power rail, which is the dominant one in this case. So I can turn that off for a faster simulation here, and then I can run. And you can see that when this simulation runs, DCIR drop runs very fast. That's why I like to use it, because I don't have to wait long, and I can check that my setup is working. I am getting voltage or power from my VRM to my sink. When this simulation finishes here, you can see it's actually already done. Boom. Completed, and it's less than about 20 seconds. And now we can go look at the results. The overview does a real quick look at the voltage drop from the VRM to the sink. It looks at the voltage drop relative to the ground at the VRM. Internal here, you can also look at the voltage drop across the sink, or across the load. From the power rail to the ground pins right there at the sink. And we can also see the voltage drop, millivolts of voltage drop across our inductor. But more interesting, you can also export or use these results in tabular format, or if you go to the vias, what's interesting here is we can actually look at the maximum current, and we can look at our turn off our components here. We can hide the conductors, and we can look just at the VCC-INT power rail, and we can grab that 3D view here, and with just a click on one of these vias, we can see which via is actually pulling the highest current. And we can also see there's one at the FPGA, and there's also one over here at where the VRM is coming in. So a quick way to start kind of look at how good is your layout. Are there some vias that you might want to take a look at the current density on? But also, with this DC analysis, we can also look at the current density and how the current is actually flowing on the power rail here to get from the VRM. And I can highlight my VRM pins here just by clicking on my VRM, I can see the pins that are delivering the current, and then the sync pins that are receiving that current. And we can see how it flows between the multiple layers of the printed circuit board and across this power plane here to get to the load. So that's, we're done. That was the DC analysis. That was really quick. And the best part about the DC analysis is I can just right-click and say copy to an AC analysis. So this is the benefit of having everything in one tool here. I don't have to change tools to go from DC analysis to AC analysis, and I just copied my whole setup. So my VRM is still there. I'm going to unload the results there. If I look at my VCC int power rail here, I can see I still have my VRM set up. I still have my sync set up. And the next thing I need to do, though, is I'm going to be looking at the AC, and I need my capacitors here. So what I'm going to do is I'm going to select both VCC int and my VCC int power rail and ground. And that's my capacitors are connected to VCC int and ground. And if I highlight both of those and right-click, it says select instances exclusively connected to those selected nets. And there's 28 of them. And if I do that, I find all of my capacitors. And I can right-click on those capacitors and say create models for analysis. And this time I'm going to put those in the AC analysis. And I can look at my board here. So I've highlighted all of my capacitors. I've brought them into my analysis. And what's interesting is if I double-click on one of those capacitors, I find that there's a library cell. There's already a model there. How did that happen? Well, let's go back to my ADS schematic that I had that's showing I'm sorry, I have to find that. I've got a few things set up here. I'm going to go back to my ADS schematic. This is my hierarchical schematic. We just already did a DCIR drop of the board that we imported, but where did the capacitor models come from? Well, you're going to learn today how important it is to actually have a good model for your components in order to look at the impedance of that power delivery network. And the first thing that we want to talk about is I needed a model. I needed need to understand how much mounting inductance that capacitor has. And so here is an example of actually measuring the mounting inductance of a little characterization board for the capacitor and creating an RL model for it. So when I say what's the mounting inductance, if I take and measure just from the plus and minus pads of a capacitor together and look at what that mounting inductance is, what you'll notice is it's a short, so at DC it just looks like a resistor, but at higher frequency there is some inductance to how that capacitor, the size of the capacitor and how it's attached to the printed circuit board, and that has some inductance. And it turns out if you measure that mounting inductance, it can be modeled as a simple RL model. And that you can see here, I believe the measurement is in red there, and then the blue is your measurement. And so that shows the correlation of a simple RL model to capture that mounting inductance. And the next thing we do is we take that measured mounting inductance and we have a measurement of a capacitor, but it includes the mounting inductance. So what I do in ADS is I create a capacitor model with a few lumped element RLC models here, two in parallel, and I put that mounting inductance that I measured from that model to ground. So now I can create a model that has that mounting inductance that I measured in it, and I can tune the parameters so that the simulation, my simulated model matches with measurement. And you can see here the blue is my tuned model, and it matches very well with this measurement, even has the little kink here in it, and that's why I have those. It's not just a single RLC component. I have two in parallel, plus that mounting inductance. And so now I have a very good model of my capacitor. And this is the exciting part. Now, if I want to connect this to the EM model of my printed circuit board, I don't want to double count this inductance. So what I do is I can now put that model into a schematic, and I can delete the mounting inductance. So now I've taken the mounting inductance out of my model, and I can compare it to my measurement with the mounting inductance, and I can compare it to the measurement that the vendor gave me, the model that the vendor says I should use. And this is where it gets very interesting. The vendor gave me a model that I said I should use, and look at this. Its inductance is higher than what I measured, and it's much higher than the model I need for attaching to my printed circuit board EM model. My EM simulator is already calculating some of that mounting inductance, and I don't want to double count. So here you can see in this case, for this 47 microfarad capacitor, the vendor model was estimating too much inductance. I measured the capacitor, and then I created a model that allowed me to remove the mounting inductance, and the blue is truly the parasitics of that capacitor without the mounting inductance. And that's what I want for connecting to my EM model. So how do I do that? I take that model, and I actually create a schematic. And here's my model. It's a schematic that this is the model I'm going to use for that capacitor. And where do I put that schematic? Well, in ADS main window here. If I go to the ADS main window, I can see the folder where my board was imported. And I can see this is the import folder with all of the components. And down here with that 47 microfarad capacitor, the import brought in the ports and layout for that capacitor. And if I add a schematic and a symbol, then PI Pro will automatically pick up that model, and I don't have to do anything. So if a schematic and a symbol exists in my component library here, when I open up SI Pro and use that component, it will automatically populate with that library cell. And so that's how easy it is to get measured models into PI Pro and have it automatically set up for you here. So all of my capacitors have models in there. I can go to the options, and I can say maybe adjust this to 1 gigahertz for the frequency range that I want to simulate for. And I can also go to my options and say use mesh domain optimization if I want to, instead of cookie cutting can leave a lot of artifacts and cause problems. So we actually have the ability to tell the simulator to look at the mesh cells that aren't significant and use sort of a mesh domain optimization to make the EM simulation problem smaller. And so then I can go ahead and just simply click Run. This takes about 30 minutes. This is a fairly large board and multiple layers, but in about 30 minutes, you can get the results. And here you can see this is the results of AC capacitors. This is be interested in what is the impedance versus frequency, but really cool, this is a FEM simulator. What that means is all of the ports are brought out. So I can change capacitor values and not have to resimulate the EM. That EM model brought all of the ports out. I can change the capacitor values, and I can also disable all of the capacitors. So here I've turned all the capacitors off, and I can open up my VRM. So I'm not connected to a power supply. That means that I have real high impedance at high frequency. But what is this downward slope? This is a bare printed circuit board, and I'm measuring the power rail impedance with no power supply on it, no capacitors. And what you're seeing here with this downward slope, that's what a capacitor looks like as you increase the frequency. And it turns out if I put a marker on that slope and look at the capacitance, it's about 3 nanofarads of capacitance that we're seeing between the power and ground layers of this printed circuit board. And that actually matches quite well with the measurement we took of the board. But even more interesting, this is one way of sort of validating if your model's correct. That's a fairly simple measurement to take. But you can also now run decoupling capacitor optimizations and look at whether your capacitors are the correct values for flat impedance. But also, after I'm done with that EM simulation, I can also do an EM simulation to solve for specific frequencies. And here you can see I am plotting the current density and from that EM simulation. And down here in my current density plot, I can change the frequency. So I've simulated the EM current density at different frequencies. And what you notice is at low frequency, the current is coming from my VRM, from the VRM side, and it's coming into this power rail on the inner layer and delivering power to the FPGA. But look what happens as I increase the frequency. And this is very important. We'll learn more about it today. The power starts to come from the decoupling capacitors. They're not filters. They're actually providing the power at high frequency. So this is 100 kilohertz, and now we go up to 1 megahertz, and you can really see where the power is coming from at these different frequencies. And at 3 megahertz, there's some capacitors on the opposite side of the board, or opposite side of the FPGA here from the VRM. The VRM is doing very little right now. It's mainly the decoupling capacitors that are providing the current. So that's something to remember is as you go up in frequency, the power supply cannot keep up. And you really have to look at how the decoupling capacitors are delivering power to your FPGA. So now that we have the EM model and we've done some looked at some of the results, what is very powerful is after finishing that AC analysis, I can go into this AC analysis and click on Generate Subcircuit. This actually creates an S-parameter model with all of those capacitor models in it for doing a power integrity ecosystem simulation in a schematic. And so if I click on that and go back to my ADS hierarchical schematic here, we can see what that exported model looks like. It actually looks very simple. It just has a VRM connection, a load connection at the FPGA, and then I actually do have a measurement port here that I put on one of the capacitor locations. And if I push in there, I can see here is the full 3D or the EM S-parameter EM model. This is stored typically as a touchstone S-parameter file with all of the ports. But more importantly, it's already connected all of those capacitor models. And if I push in there, you can see you can actually switch between different models. You can have a lumped model. We could also use a vendor S-parameter model, or I can use the measured model that I created. So some different options there to switch between. Very powerful sub-schematic here, and all of that is nicely contained in our ACEM model of the power delivery network. And where do I use that? I can now just take that simple model of my printed circuit board power delivery network, and I can put it into a PI ecosystem simulation here. And in this case, we were looking for worst case power delivery noise on this power rail, and to simplify things, we actually hooked it up to a bench supply with a Vicor module current multiplier to make sure we had a matched impedance with the original VRM. But this basically let us monitor the current going into VCC-int. We delivered that current into our power delivery network here. And then for the load, we have a package die model. The vendor, Xilinx, provided this package die model. And then what we wanted to look at first is we can actually run an S-parameter simulation and say, what is the impedance we're seeing? And this is where it gets interesting. If we run that S-parameter simulation, we can see that impedance versus frequency, this is what the what it looks like on that power delivery network. At DC, the bench power supply is maintaining a constant impedance. And then in the mid-range, we have our decoupling capacitors. But what's interesting is if I try to measure at the bottom of the FPGA, the vias going to the FPGA, getting from the bottom of the FPGA up through the board, have a certain amount of inductance. And if I measure on the bottom of the FPGA, I only have a single via that I'm trying to go through sometimes to get up to the power plane. So that has some inductance. Measuring at the VRM, I'll see a certain amount of inductance there. And if I measure at the package pins, I'm still not seeing what the die sees. So with simulation, with this package die model, I can actually look at the impedance seen by the die, and it's a place where I can't measure. But in simulation, I can clearly see in this black trace that there is an impedance peak at about 30 megahertz. And so what I can do is I can create a stimulus that turns on and off the load, the current, at 30 megahertz, and that's this red. You can see the current pulsing on and off at 30 megahertz. And then the blue is the current that actually is at the FPGA pins, and then the black is the current at the VRM. And this is all done with the simulation. And if I go back to my power integrity ecosystems here, you can see to do the impedance measurements, I simply attached a 50 ohm port here. This is exactly how we do it in measurement. You'll learn more about that today. And out here for transient, I set up a pulsed current load here, switching on and off at 30 megahertz. And this simulation then provides me with not only impedance data, it also provides me with the transient ripple. So let's go back to our presentation, and we'll talk a little bit more about the results here. Okay, perfect. So we just showed you the results from this power integrity ecosystem simulation, and I hope you found that interesting, how quickly we were able to go through that setup and show you how to find the worst case noise. And here you can see exciting at 30 megahertz. We found that impedance peak. We excited it with a forced response, and clearly with simulation we're showing that worst case. We also found this with measurement that 30 megahertz, we were able to toggle those 400,000 flip-flops within the FPGA at 30 megahertz on-off toggling, and we were able to verify that this is larger noise than at 200 megahertz. I also want to point out that we talked about flat impedance is important. That impedance peak was really where we were finding the worst case noise. So if we want a quiet power rail, we want to avoid those impedance peaks. And this is an analysis where you say, well, target. What is in simulation, you can actually find out the ideal stimulus of exciting all three of these peaks at different phases, and you can find the worst case ripple. And that's exactly what we did with our schematic simulation here in ADS. We set up a model that created those three impedance peaks in the power delivery network, and then we did an optimization to find the maximum forced response by turning on each of those three resonances, exciting each of those three resonances. And here you can see the results. We start the first frequency by exciting with a forced response. Then at the peak of the first frequency, we start the second frequency. And at the peak of those first two, we start the third frequency. And even though each one is below a target impedance and should not cause an excessive ripple, we see that if they all line up on top of each other, called a rogue wave, we can actually get a rogue voltage wave that could exceed our target ripple or our ripple specification. And this is actually not just something in simulation. Steve Sandler of Picotest took that excitation that was figured out by simulation, that worst case excitation, and downloaded it to an arbitrary waveform generator and actually excited the power rail with these impedances and was able to capture a live rogue wave on this voltage regulator board. So in summary here, we really want to talk about not just waiting till the end, till hardware arrives and to see whether we have ripple on our power rail. We really need to do a little bit more investigation, and if we can design for flat impedance early on and select the right components and voltage regulators, modules, et cetera, we can really ensure quiet power delivery and make our life much easier once the hardware is built. And so here you can see it's important to have measured models. The pre-layout simulation, you saw some cases here where we're able to do a lot of sort of lumped models and analysis up front. We can very easily bring in the printed circuit board and get a higher fidelity model with all of the PCB parasitics. And then we can bring that EM model out to a full ecosystem simulation and actually predict worst case noise. We can look at things like the impedance that the die sees using that package die model that even measurement can't get us that information. And so we really need this full PI ecosystem to ensure a quiet power delivery. So don't wait until measurement to find you have an EMI failure due to power rail noise. Starting at post layout and just checking the power integrity often is just optimizing a bad design. So we really want to start early with pre-layout, power integrity, and power electronics simulation and modeling. I do want to cover some of these key important points here. And the first one is target impedance and how to find it. I often get people saying, okay, I understand this simple target impedance question, but how do I really calculate it? And if we go back to that target impedance, you'll find that the specification for the maximum amount of ripple is usually in the data sheet. It'll be very clear that this load can only handle a plus minus amount of ripple on the power rail. But what is the delta current? What is that transient current that my load is producing? And oftentimes that is not in the data sheet, and so a very, very, very rough rule of thumb is about 40 to 60% of the maximum DC current. So you look at the max specification on the data sheet for your load for DC current, and you take about 40 or 60% of that. But there's also some other ways to look at it. And we're going to learn that here. So first of all, okay, we can do that rough estimate of what the delta current is, but what's the spectral content? And what is it that's causing the ringing on our power rail that we really need to avoid? And so if you look at, we want this flat impedance, we want this quiet power delivery, we don't want any resonances. So we really need to try to manage what causes those resonances. And we look at inductors, store energy in the magnetic field, capacitors store energy in the electric field, and if you get the current or that energy flowing back and forth between them, you can actually create a resonance like a swing between potential and kinetic. And in the electronics world, we have some very simple equations to describe that sort of resonance when we have an inductor in parallel with a capacitor. And up here in the left corner, we see that I've modeled my voltage regulator as a resistor in series with an inductor. That means at low frequency, it looks like a resistor. At high frequencies, though, at a certain point, it can't deliver power anymore. My VRM has a limited bandwidth, and it starts to go higher in impedance and looks like an inductor. But what's interesting is that inductor of the VRM, that active inductor, this isn't really a real value, it's an active inductor of that control loop, is in parallel with the first bulk capacitor. And if we don't choose that bulk capacitor correctly, then these equations for how it will resonate shows us that we can have a big problem. The impedance versus frequency if I simulate that simple inductor in parallel with a capacitor, for instance, this 6 nanohenries of active inductance in parallel with this 100 nanofarad capacitor ends up with an excessive impedance peak. That impedance peak is the characteristic impedance of that inductor and capacitor times Q. And if you look at Q, this is important, it's dominated by, okay, I can lower the impedance to reduce the Q, the characteristic impedance, but more important, the real resistance of that resistance in the VRM and the ESR in the capacitor. Those two real resistances, that's what, if I increase the ESR of my capacitor and if I increase the resistance of my VRM, I can actually reduce that, the Q or the sharpness and the peak height there. So this is where it's important to understand that capacitors with the lowest ESR possible and VRMs with the lowest impedance or resistance possible may not be what you want, because it will make these resonances worse. It will create larger peaks or anti-resonances. So be careful with how you pick your ESR of your capacitors and the VRM resistance, because the lowest possible is not always what you want. You want it below the target, but not too low. And to kind of explain how this works for a power delivery network, let's just start real simple. We're going to start with a power supply, and here's what it looks like in the impedance versus frequency domain. It's a resistor at low frequency, and then it goes upward in impedance and looks like an inductor. So this is the RL model of a VRM. We just simulated it with a simple SPICE type transient simulation, and that's what its impedance looks like. Notice it has high impedance at these higher frequencies. When I go over to my transient simulation and hit it with a step load or a forced response, the step edge has higher spectral content. There's no power at the high frequencies. So I get a droop and a kick. I get this large ripple on my power rail whenever I have this step edge with the higher frequency content, because I don't have any power delivery at the higher frequencies. I need to do something about that. I need to add a capacitor that can provide that charge delivery at the higher frequencies. But I want to pick the right capacitor. My impedance is a capacitor that decreases in frequency and provides a flat impedance. And it turns out it's a very simple equation. The capacitor I want is simply that active inductance of the supply divided by target impedance squared, and that gets me really close to the exact value of capacitance that I need. If I install that flat C capacitor that's balancing the inductor, then you'll see here on the transient simulation, I get the blue response. No ripple on the power rail. That looks great, very quiet. But there's a problem if you look at how capacitors are modeled, and if you measure them, you get a capacitor, which you pay for, but you also get an inductor for free. So at higher frequencies, the capacitor actually looks like an inductor. And right where the capacitor and the inductances cancel each other out, the capacitor region, your voltage lags the current. In the inductor region, the voltage leads the current. But right in the middle, voltage and current are in phase. That's purely resistive. That's the ESR of the capacitor. So understanding that capacitor doesn't stay capacitor forever, when we add that 16.4 microfarad capacitor to flatten out the 15 nanohenries of inductance that we see here from the VRM, we can extend the flat region only so far. And then we have, in this case, 875 picohenries of that bulk capacitor. So our bulk capacitor now turned inductive, and we need to find a smaller capacitor with less inductance to go to higher frequency. So again, we use that real simple equation. We take that inductance of the bulk capacitor divided by target impedance squared, and that lets us know what our next smaller capacitor is. I can definitely find a 1.5 microfarad capacitor with less inductance than the bulk capacitor, and that lets me go out to an even higher frequency range. The next question is, this sounds great, but how high a frequency do I need to keep going? I can't go forever. It gets very difficult to start finding capacitors with low enough inductance. I may have to parallel a bunch of them together, etc. So the next thing I do is I look at the package die model from the vendor. I ask the vendor, can you give me an S parameter model of what the package and die power delivery network looks like? And here, this is a S parameter model from Xilinx, and I simply am looking at the impedance seen by the die when I connect this package die model, this S parameter, up to 3 different cases. I hook the package up to a short. I provide a dead short, the best power supply I can ever provide. That's the bottom green trace. I hook it up to a matched impedance of about, I think, 15 milliohms here. And then I also leave it open with no power supply connection. And that's the blue trace of impedance versus frequency here. And with no VRM, that downward slope is the capacitance of my package die model. I can actually measure how much capacitance or charge storage that package can deliver to the die. And at high frequencies, if I go up high enough in frequency, it doesn't matter what impedance my printed circuit board and my VRM have, the die does not see that difference. All it sees is the impedance internal to the package and the die. So above a certain frequency, it doesn't matter what I do on the printed circuit board, and I can actually stop probably worrying about adding capacitors to go up to higher frequencies. You can also do a transient style simulation where you put in 10 millivolts of noise on your package pins with this S parameter model and see how much noise gets to the die. And if I look at that transfer function, at low frequency, 10 millivolts of ripple goes straight through to the die, 1-for-1 transfer. But then at high frequencies, we can definitely see that the package is filtering away that spectral content. So again, at high frequencies, I don't have to provide power delivery because it's not going to get into the package. So this is another way to look at that. I was just talking about, what frequencies does our printed circuit board need to deliver power, and the simplest way to show that is I take that RL model for the VRM, which is the black trace. I take the S parameter model for the package die, which is this red trace here of impedance versus frequency, and I literally connect them together in a schematic and measure the impedance that the die sees when the package die model is connected to the VRM. No decoupling yet. And without any decoupling capacitors, the inductor of the VRM has a parallel resonance with the capacitor in the package, and I get a huge impedance peak. This is why we need decoupling capacitors. If I excite this impedance versus frequency, this schematic model, with a step edge and a forced response at that peak, I can definitely see I have a lot of ripple on my power rail in this time domain plot on the right. Now, most people would say, oh, I've got an impedance peak at that at a specific frequency. I'll grab a capacitor that has super low impedance at that frequency and bring it down. And the problem is, if you just grab an off-the-shelf, maybe 100 microfarad cap or something that has low impedance at that impedance, you may be causing more problems because the inductor will maybe create an anti-resonance with the capacitance of that capacitor, and then that capacitor's inductance may be still resonating with the inductance of the package, and you get 2 peaks. So I added 2 capacitors. Now I may need to add I added 1 capacitor. I may need to add 2 more capacitors to try to get rid of those anti-resonances, and I sometimes call it the whack-a-mole problem. Because you're trying to keep beating down those anti-resonances. If you use that simple equation, the capacitor I need is the inductor divided by the target impedance squared. Maybe I get lucky and I only need 1 capacitor to flatten out the impedance and I avoid those anti-resonances. So that's the beauty of the flat impedance. And we're really wanting this blue trace over here of quiet power delivery and very little ripple in the time domain. And we can see with those two impedance peaks, if we pick the wrong capacitor, we can get the black where the forced response has a fair amount of ripple. So in summary here, if we go back and look at applying this concept of looking at the impedance to understand what capacitors I need and what I need to do on my power delivery network, we can go and look in the impedance domain at what's happening at 30 megahertz. And this is very interesting. If I actually wanted to try to reduce that resonance at 30 megahertz, I can't change the package. That's sort of fixed. But on my printed circuit board, I noticed that if I have a short, if my impedance is too low, that anti-resonance is actually higher. But if I can match the impedance, I can find sort of a matched, optimized 5 milliohm impedance that matches the load better, and it actually brings down that impedance peak. So that's something to consider. I'm making that real resistance higher so that the characteristic impedance divided by that real resistance, or the imaginary impedance divided by the real impedance, reduces the Q, or the impedance peak of the resonance. So just reiterating that you don't always want the lowest impedance, because that might create this impedance peak with the package inductance. So here's a polling question. In the digital world, we use a rule of thumb that, and then this is sort of a challenge, just kind of, it's a very important concept, and I think a lot of people don't really realize where the equation comes from. But in the high-speed digital world, we like to say, you know, what is the spectral content for a digital step edge? Well, they have this rule of thumb that says, well, it's 0.35 times the rise time. But what they always seem to leave out is this for a 10% to 90% rise time, or is it for a 20 to 80% rise time? So if you're following along, and we just talked a lot about how, you know, understanding impedance versus frequency, and, you know, we have a dynamic load, and what is the spectral content of that dynamic load that's switching on and off. Well, if you try to create that dynamic load, you're going to need to define the rising and falling edge. And a lot of times you pick that rise time based upon what's the spectral content you're looking for. So is 0.35 time or a 2080? And I'm going to push that polling question out to you. And if you guys can go ahead and click on your answer for 0.35 times the rise time, which rise time measurement should you use, 1090 or 2080? Okay, it looks like we've got getting close to about half of the people responding here, so that looks good. And I'm going to go ahead and start looking at the answer. And we have a lot of smart viewers today. And yes, 1090 is the right answer, so it's nice to see we have some experts out there. It actually comes from the RC tank circuit. If you go through the math of looking at how that capacitor charges up with a voltage input on that RC tank circuit, and then you solve for the time to reach 10% and the time to reach 90%, and if you look at how the 3 dB frequency point is defined relative to that RC resonance, you'll find that it works out to be 0.35 divided by the 1090 rise time will give you that 3 dB sort of bandwidth of spectral content. If you are doing 2080, which is what the high-speed digital world uses a lot of times for rise time, then you actually want to use 0.22 times that rise time to get the bandwidth. Okay, next, how to model the DC to DC converter. So we're running along here. I might have to jump ahead a little bit. This, how to model the DC to DC converter, is actually part of a how-to video. Steve Sandler has done a whole series on YouTube sponsored by Keysight, and it's how to design for power integrity, doing DC to DC converter modeling and simulation. And I highly recommend watching this video. So this is the video that we're talking about, how to design for power integrity, DC to DC converter modeling and simulation by Steve Sandler. And that is on YouTube if you want to watch the full thing and see the or download the workspace that goes with it. And I wanted to highlight some things from that video. Steve talks about a lot of voltage regulator modules. He talks about the importance of being able to model that VRM and see how it impacts your design. How does the output impedance impact it? What's the operating efficiency? What's the switching frequency? What's the power supply rejection ratio? Well, how do you model that? Because a simple RL model is not going to give you all of that information. And so Steve, he's written a book on switch mode power supplies, and he talks about using a state space average model. This is basically just, in the mechanical engineering world, uses state space models a lot. Instead of solving the full differential equation, they just define they have a couple of equations that define the states. And in the case of these voltage regulator modules, we're defining that pulse width modulation, that DC to DC conversion with states equations. And that model can be captured very easily within a schematic. And with a few simple measurements, you can actually tune that model to match with the VRM that you're working with, that you've measured. And that model then enables you to look at AC sort of output impedance and extracted loop gain. You can also look at spectral content for the large signal switching, ripple spectrum, power supply rejection ratio, and you can also look at time domain characteristics in terms of ripple and inductor current. And again, it's just reiterating that a power supply is actually a control loop. And in the case of the DC to DC converter, it's not an easy circuit to model or to get a full SPICE circuit for this pulse width modulator and your upper and lower switch FETs. To get that full model would run very slow and transient, and so that's the reason for actually doing more of a behavioral model. We really don't need the transistor level logic model. We need a little bit higher order behavioral model that lets us run more quickly with the full power integrity ecosystem simulation. And this type of model, you can see here, it defines the states, state 1, where you have the upper switch on, lower switch off, state 2, upper switch off, lower switch on. And there is a third state, which is sort of the discontinuous mode, where both switches are off. This type of model can handle both continuous and discontinuous operation. And again, if you go through the math, you can start defining, we take those state equations and we can start defining construct a continuous state averaged output for the inductor current and the voltage there. And here you can see that model. Basically, those state equations are contained in the modulator block, and that also has the slope compensation that is with the ramp that is modulating, pulse width modulating for the duty cycle. That block is then added, or was it, so that block is then used with a feedback amplifier system. This transconductance amplifier provides the feedback. So you do need to kind of check with your data sheet for your VRM to see what kind of feedback system it's using. And this, along with your output inductor and your capacitor, create your full state space average model of the VRM. Now you can, and Steve has actually gone through and done all the algebra to look at an analytical solution for power supply rejection ratio and the output impedance, and he notices that V ramp and RI are sort of these sort of dominant terms. And if I can get a measurement for VRAMP and RI, then that will pretty much help me get the model matching, or my VRM model matching with measurement. And so in the how-to video, he actually steps through an example of characterizing a voltage regulator module board, and he shows how you can measure that RI variable by looking at, if there's a V-comp pin, you can vary the output load current and look at how the comp pin voltage changes. And if you get that slope of V-comp versus output current, you can then determine RI. But that's not the only way to get things. You can also find from those equations that the output impedance is very dependent on RI. So you can actually use the schematic itself with this VRM model and tune RI until the output impedance matches with measurement. And so here you can see the DC level of my simulation in red is tuned to match the measurement by adjusting RI. And that's another way of determining RI using my output impedance measurement. You can do a direct measurement of VRAMP if they have that VRAMP pin brought out. In this case, on this regulator here, there was a VRAMP pin that you could measure. You have to be a little bit careful that you don't damage the circuit by measuring at that point, but it is possible. But again, if your VRM is completely packaged up and you don't have any access to that VRAMP pin, another way of doing it is actually measuring the power supply rejection ratio. This PSRR value, tuning that, and RI will allow you to, I don't want to say tuning VRAMP to get a match with PSRR is another indirect find that your state space model working, and it's actually finding the instantaneous duty cycle for the power delivery to your load, and that instantaneous duty cycle can then be used with a sawtooth ramp to switch to modulate some switches here, and that's actually what gives you your large signal transient ripple. And so we use the state space model to give us the instantaneous duty cycle that then can modulate our switches and give us the large signal. And if we do that, if we connect the state space model up with our EM model, we can actually get a simulation and measurement to agree quite well in terms of predicting that switching ripple. And here you can see the complete model, and when we run that simulation, you can see here's the results. We get both small signal and large signal results. The switching ripple is overlaid with measurement. Our impedance, AC output impedance, we've got the simulation and measurement looking pretty good there. We can also look at things like extracted loop gains and power supply rejection ratio. And again here, we have, again, those hierarchical schematics, so you can actually run those, download those workspaces and give these state space models a try. And you can even parallel the models and do multi-phase DC to DC converter analysis. I'm going to skip a few here, and we'll wrap up, and then I'll have room for some questions, okay? Okay, so the next one, this is just talking about why we need EM models for the printed circuit board. And I think you saw that in my demo earlier, how important it is to actually capture the parasitics and the distributed nature of how the printed circuit board is delivering power at the high frequencies. I think very illustrative of that was the fact that I was showing actually which capacitors were delivering power at which frequencies and where they were located and how that power gets delivered. This is also part of our how-to videos on optimizing decoupling capacitors, and there's some content there to really show you why you don't want to use SPICE models, why you really want to do an EM model of that distributed parasitics. And we also, along with explaining the importance of doing those EM models, we also do a lot of, there is a whole video on how to measure capacitors and create those models. And I showed you that earlier, how we use that measure-based model with the mounting inductance removed to really create a high-fidelity model and have the accuracy we need for simulating the power delivery network. And we do have this how-to video that shows you how to do that measurement, because when you do the measurement, you can't just do a one-port impedance measurement. The network analyzer does not have the sensitivity to do that. And so we use what's called a two-port shunt impedance trick, where we excite with port 1 and port 2 is actually doing the measuring the small signal. And you can see here the blue is what is the real data. The red is a one-port reflection measurement that doesn't have the fidelity. And I was going to jump, here's the picture I want to show you. So this is actually, you can actually do an EM analysis and show how this two-port shunt impedance is really exciting with port 1, and then the small signal that gets through to port 2 gives me the sensitivity I need to actually measure down into the micro-ohms of impedance. And you can see here, this is measuring that short and looking at the mounting inductance of the capacitor pins shorted together. And so very cool things if you want to look at that video on how to measure and model capacitors. That one is very practical, and we do get a lot of questions on people asking that. And then finally, I do want to iterate for reducing EMI by design. A lot of people want to know, what filter can I add? What shielding can I put on to get rid of my EMI problem? And I really, really want to emphasize, I really hope that people don't wait until hardware is built to try to pass their EMI tests. And I really want people to start thinking of early on in the design. Don't forget about your ground net. It's one of the largest nets. It connects to everything, and yet on a schematic, it's only given a simple symbol and used in a lot of places. But remember that that ground net is really quite complex, as well as the power nets, and really the EM simulations enable you to really understand how those nets are connected together and the real parasitics of that power distribution network. Remember that if you do a high fidelity sort of state space average model, a behavioral model of your VRM, you can get at things like optimizing your power supply rejection ratio and actually looking at what's the large signal switching noise, which a simple RL model is not going to do for you. And here you can see this is a C-ramp capacitor that is optimized to provide the maximum power supply rejection ratio using that state-spaced average model. Again, emphasizing how we found the worst case noise by finding the impedance peak, and it was only when we connected it to the package die model that we saw this worst case impedance peak. And we now realize that maybe if we decrease, or was it, if we optimize the impedance of our power delivery network on the printed circuit board, we actually might be able to bring that resonance down a little bit, since we can't change the internal inductance of the package. Okay, with that, I'm going to go ahead and jump to our summary here. Like I said, really a good idea to try to watch those how-to videos and really learn about this full process that I'm describing here today. Just want to emphasize the advantage of doing sort of a full power integrity ecosystem workflow. I talked about this earlier, but I really feel it's important to get good models, start with some pre-layout simulations so that you understand the problem, and then bring in your EM and look at the full power integrity ecosystem and simulation before you start really, jumping to the full hardware and measurement. So again, here are the 5 how-to videos. There's actually a book that Steve Sandler has done to capture, if you like to read rather than watching the videos, he has also captured it in book form for all of those videos, and that's on Steve's website. We also have Keysight. We have both simulation and measurement with our PathWave ADS simulation capability that we've talked about today. We also showed you the two-port shunt impedance measurement with our network analyzers, the E5061B, using power picotest accessories. And then we also have the brand new Infinium MXR real-time scope for power rail diagnostics and the current analyzer CX33000 here. If you do want to try out these workspaces and try out a power integrity analysis on your design, be sure to take advantage of our world-class technical support as well as online documentation and our Jumpstart 1-minute getting started videos on the Knowledge Center. And with that, the next generation of electronics really needs power integrity more than ever. Flat impedance design improves safety, reliability, cost, size, and et cetera. So I would like to recommend that take the guesswork out of power delivery, test drive PathWave ADS with PI Pro today. Your best power integrity will be your next help with wrapping things up, and I think we are still on time. How are we doing, Carmina?
We are doing just great. Grace under pressure, just like when you're playing underwater hockey. So Heidi, there's a lot of technical questions, which I know you are always good at answering them, and I know you'll answer them via email. A lot of folks asked about the demo that you presented and getting those workspaces. And I'm not sure how much of what you shared is directly from the how-to videos, which is in the resource link. So do you want to comment on that?
So one of the things, and I think my video is still showing here, it'll pop up in a moment. We can actually share the workspaces, but the board file for the ZCU 104 board is a Xilinx content. So like I said, you can buy this from Newark. Xilinx will provide you with all the board files from their website. You can download those. We're happy to provide you the workspaces maybe without the actual board file in it, but then you could just do the import and run all the analysis. So we could actually provide this workspace for you. We haven't quite done that yet. What we have done is there is a workspace available with our power integrity boot camps that has the package die model in it. So that one we have been sharing with customers, but the actual board file for the Zinc ZCU 104 board, that one you'd have to get Xilinx permission and download that and add it to the workspace. But good comment. We'll work on following that up with our next power integrity boot camp to have that material more readily available.
Great. Thanks so much, Heidi. As usual, thank you so much for your presentation. As I mentioned, you'll have to take the rest of the questions offline, so thank you. And thanks to everyone who attended today, and thanks for staying with us. We have a number of free complimentary events. You just go to that website that's on the screen, www.keysight.com/find/events, and also fill out the survey. Let us know what you need. Let us know if you want to talk to a technical expert like Heidi. And stay well, and thanks so much, Heidi.
Thank you, Carmina. A great job, and appreciate your support.